Hello everyone, my name is Mustafa Amara. I'm presenting today our paper titled MEC-enhanced Information Freshness for Safety Critical C-V2X Communication for the ICC Clean 2020 workshop on behalf of my colleagues Miltiades Filippo and Darius Abella. Let me start with the agenda. I'm gonna first discuss the introduction, motivation of our work. Then we're gonna go into the system description and system model and the problem statement. Afterwards, I'm gonna try to go briefly over the information freshness, how to compute it, and what's the difference compared to the other typical latency-related metrics. Some numerical evaluations are gonna be discussed, and I'm gonna conclude with some summary, key points, and future work directions. Let me first start with the introduction. For the current 5G systems, especially for the Vehicular-to-Everything or short V2X communication, we have a plethora of reliably functioning sensors for the V2X. So this is expected to exist, providing environmental perception via exchanging critical messages among vehicles, pedestrians, and road infrastructure. So in the figure shown below, we have a number of vehicles communicating with each other, communicating with the different network components, and also communicating with different road users, for example, pedestrians, motorcyclists. From the network side, we have roadside units, eNode Bs, edge cloud, and the back end. Our main objective in this work is to investigate the information freshness, so how much the system knows about the surrounding environment for a V2X wireless services. Information freshness is quite critical for the V2X services, especially when we're talking about services like road safety and driving experiences. Focusing on the C-V2X technology, the architecture of the cellular network is expected to have a vital impact on the support of delay-intolerant V2X services. So the motivation of our work is as follows: focusing on the VRU use case and focusing on a freeway road environment, which would try to model the worst case information freshness, termed peak age of information, with and without the multi-access edge computing, short for MEC, co-located at the radio network nodes, so the eNode Bs. And then based on the proposed models for the peak age of information, we investigate the VRU's densification and effect of other system parameters with and without MEC infrastructure utilization in our network. Now, moving to the systems description, as I mentioned, we are focusing on a freeway scenario. So what we have here in the picture is a two-lane freeway scenario with a number of eNode Bs deployed on the side unit. Those eNode Bs are equipped with MEC servers physically co-located with them. They are serving a number of VRUs physically co-located at a service point. And in terms of the message generation, we are looking into VRU that are generating periodic messages. Such periodic messages can mimic the Corporate Awareness Message, short for CAM, or the Decentralized Network Message, short for DEM. Also, we try to look into how can the users or the VRUs utilize the given computational proximity provided by the MEC service. Such computational proximity intuitively should alleviate some of the network imposed latency, as we will see later. In the model that we adopted for the periodic message generation, as shown in the figure below, we show it only for two VRUs. There's a time window which is denoted by this T. Throughout this time windows, packets are generated periodically but randomly. So periodically, which means every T a VRU has to generate a packet. Randomly, that the exact offset, which is a tau, it's not fixed for all the users. So in the first part, or for 0 to t-1, we have two VRUs generating with two different offsets. In the second one, we have a collision between the generation offsets. In the case of this collision, we have an equal sharing of resources for VRUs. So one aspect we're going to investigate is the effect of the VRU densification on the available resources. We consider in our work an uplink cluster transmission, which means that for every VRU, we define a cluster consisting of the k closest vehicles, as shown in the figure below. So every VRU is interested to convey its message through the UU interface to its cluster. Now, moving to the age of information. On the right-hand figure, we show here the age of information as a function of the time. Age of information basically is a metric that tracks the information freshness of a system. So in simple terms, it grows linearly in the absence of successful transmission updates. So once a packet is generated, the Ageof Information tracks the age of this packet till it's successfully received at its destination. So successful reception point is depicted in the figure by the red arrows. The generation point is depicted by the green arrows. So the Ageof Information gets subtracted or gets decreased by the difference between the current timestamp, which is t, and the time at which the packet was generated, which is denoted by this j subscript k of t. In order to investigate the information freshness for critical services, we try to look into the worst case Ageof Information, which is also known in literature as the peak Ageof Information, as it provides insights on the guaranteed system performance. Mathematically, the peak Ageof Information consists of two main parameters. First, the average inter-arrival time, which in our case is a fixed parameter, which is the VRU packet intergeneration time, and second, the end-to-end latency, which is basically the end-to-end latency through the packet that has experienced from once it was generated at the VRU side to the point it was generated at the furthest vehicle in its cluster. So the K here is basically, the K parameter represents the different VRUs, which goes from 1 till uppercase K. So in order to quantify the peak Ageof Information, we need to quantify first the end-to-end latency experienced by the packet belonging to a given VRU over all the different network components. And this is different from the typical end-to-end latency because, as we can see, the peak Ageof Information couples the end-to-end latency with the packet intergeneration time. Because remember, we're trying to quantify the information freshness of a system. So the overall end-to-end latency for the case VRU is, in our work, is basically two variants. For the first, the case where you have MEC deployed and the case where you don't have no MEC deployed. The first one, for the typical cellular case, which is without the MEC deployed, it consists of a number of parameters. It consists of the radio components, which are represented by the uplink and the downlink latency. It consists of the network latency parameters, which implicitly have the backhaul latency, transport, and the core network latency. And finally, the execution or the packet processing at the packet processing at the end. For the different ways or the different models for each of those subcomponents, I would recommend the viewers to check our paper below, which basically introduced the different models, and we verified those models in this paper. For the case where we have the MEC deployed, we alleviate the presence of the computational proximity closer to the VRU side, and we are able to alleviate the network imposed latency. So we're only governed by the radio latency, which is the uplink and the downlink, as well as the execution latency. Our evaluation objective is as follows. First, we try to analyze the effect of increasing density of VRUs on the information freshness, PAOI. We investigate the effect of VRU packet inter-arrival time, which is the T on the peak Ageof Information. We highlight the difference between the end-to-end latency and Ageof Information. And finally, we try to showcase the benefits of MEC deployment for VRU use case in C-V2X systems. Our adopted simulation parameters in our evaluations can be summarized in this table. We have different entities. We have the vehicles, the VRU, eNode B, or MEC host, and we have general radio parameters. First of all, looking into the effect of the increasing VRU on the peak Ageof Information. On the right-hand figure, we have on the x-axis the number of VRUs, and on the y-axis, we have the peak Ageof Information. We have the red curve representing the peak Ageof Information with MEC and the blue one without MEC. First of all, for the two curves, we can see that as the number of VRUs increases, the peak Ageof Information increases. This is expected because as you have a larger number of VRUs in the system, the contention on the limited number of resources increases, so the end-to-end latency basically throughout the whole different components increases. Another thing we observe is we have nearly a 61 gain or reduction in the peak Ageof Information between the case without and with MEC. This large gap is achieved due to the alleviation of the network imposed latency. So we have a lower end-to-end experienced latency for the case where we have the MEC deployed. And this in fact affects the peak Ageof Information. So in other words, we can say that the system is more timely aware about its environment when the MEC is deployed in our network. Second metric we try to look into is the effect of the VRU packet interarrival time in the x-axis here. Here on the left-hand blue y-axis, we are looking into the peak Ageof information. On the right-hand red y-axis, we are looking to average end-to-end latency. And we have distinct two regions in our results: the A region and the P region. A region goes from 1 till 30 milliseconds, and the B region is the rest. So for the A region, we have a very loaded system. It means that the VRUs are constantly generating packets with very low interarrival time. This will mean that as this T gets larger, till, for example, it goes to 30, there is always some gain, because the load in the system, the load on the available resources gets decreasing, it gets lower and lower and lower. That's why we see that the peak Ageof information and the end-to-end latency are decreasing in this region. However, after a specific point, after a specific sweet point, which is here around 30 milliseconds, we see the performance deviates. We see that the peak Ageof information starts to increasing. However, the end-to-end latency decreases. The end-to-end latency decreasing can be explained as follows. If you have basically a very high interarrival time, it means that the VRUs are not going to try to access a channel or to access the resources on a periodic basis, but on a very large periodic basis. So the load in the system gets lower, and the packets don't have to wait long to get served. That's why the end-to-end latency decreases. However, this kind of large interarrival time leads to also outdated information of the VRUs, which mean that from the system perspective, this kind of increasing of the T will lead basically to higher Ageof information, because the system is not timely updated about the status of the VRU. So this figure shows clearly the difference between the end-to-end latency and the peak Ageof information. If you have high average end-to-end latency, this doesn't mean you're always going to have a timely updated system. So that's why from a network perspective, it's not only important to look at the latency, but you have to look at other metrics which are affecting the criticality of your systems. For example, the Ageof information and the maximum value of it, which is the peak Ageof information. Now for the conclusion. As we have seen throughout this talk, we focused on the VRU use case. We provided information freshness evaluation considering two different network architectures, variants, with and without the MEC system deployed. We have also showcased a number of performance evaluation results for the different VRU densities, as well as for the packet generation times. And the key message of our work is the gain that you can get throughout the MEC deployment in your network due to the processing resource utilization in close proximity to the sites. Some of the future work listed here is to consider even more realistic modeling of different network components. And the second aspect will be to consider the consideration of different traffic environments for VRU road interaction. One example would be the VRU mobility. With this, I would like to thank you for the time. And please, if anyone has questions, don't feel hesitated to reach out for us. Thank you.